Bresenham's line algorithm is a line drawing algorithm developed by Jack Elton Bresenham. The algorithm takes 2 points and traces a line between those 2 points onto a grid. It is renowned for its efficiency due to its utilization of faster integer arithmetic as opposed to the slower floating point arithmetic. So how about we delve into how the algorithm works and how it's derived. We'll start by selecting 2 arbitrary points on a grid and drawing a perfect line connecting them. This line can be represented in the form y equals mx plus b. We can figure out the value of m as a change in y with the change in x. We can then plug this value back into the equation. We can then multiply out that delta x and further 0 out the left side of our equation, giving us 0 equal to delta y multiplied by x minus delta x multiplied by y plus delta x multiplied by b. This equation is significant in that if we make it a function of x and y, we can plug in any coordinate and the equation will return 0 if that coordinate lies on the line. We know function x0, y0 has to equal 0 since it defines a point on the line, and since it is most derivative, this algorithm only works when the absolute of delta x is greater than the absolute of delta y, and when these changes are positive. We subsequently also know that the gradient m is at most equal to 1. This means the next point on our grid will either be x0 plus 1 y0 or x0 plus 1 y0 plus 1. We can discern the better option by evaluating the midpoint of these coordinates, function x0 plus 1 y0 plus 1 half. If the value is positive, we'll increment upwards. If negative, we remain at the same level. We can establish tracker variables for the x and y axes to track these increments. However, an issue still lies within this method and its utilization of floating point arithmetic, so this isn't our solution. We can instead try using the difference between these points instead. We can define the initial difference as d equal to function x0 plus 1 y0 plus 1 half minus function x0 y0, simplified to delta y minus 1 half delta x. D will act as our decision parameter, where if d is negative, we remain at the same height, denied by incrementing only the x tracker, and set d equal to function x0 plus 2, y0 plus 1 half minus function x0 plus 1, y0 plus 1 half, simplified to delta y. If d is positive, we increment upwards, denied by incrementing both trackers, and set d equal to function x0 plus 2, y0 plus 3 halves minus x0 plus 1, y0 plus 1 half, simplified to delta y minus delta x. All equations can then be multiplied by 2 to remove the floating point arithmetic. We can then generalize the second and third equations for each iteration by accumulating their values onto the decision parameter. Rounding off the method, we can use our trackers to capture the points we need to draw to by summing their values onto the initial point per iteration. Summarizing the method, we begin by selecting 2 points on a grid, calculating delta x and delta y and establishing trackers x and y. We then set a decision parameter to an initial value of 2 delta y minus delta x. If the value of the parameter is positive, we add to both our trackers and sum 2 delta y minus 2 delta x onto our parameter. If negative, we add only to the x tracker and sum 2 delta y onto our parameter instead. We then sum these trackers onto a base position, giving us the next point we need to draw to. We subsequently repeat this comparison and drawing process for the remaining horizontal length of the line, drawing a line between the 2 points. We then need to remember to draw to the initial point as well, finishing our line. As stated previously, issues still remain with this algorithm, with failures in cases where the absolute of delta y is greater than the absolute of delta x, or when these changes are negative. To fix the latter, we can invert the increments, so if delta y is negative, we instead increment downwards, and if delta x is negative, we increment to the left. The former, a bit more complicated, will see us flip delta x and delta y so that delta x is equal to delta y and delta y is equal to delta x, this acting to have the method treat the line as if delta x were greater. We can then iterate through the method as usual, but when drawing to a point on our grid, we will instead sum the x tracker onto the y coordinate and the y tracker onto the x coordinate, flipping the line back to its intended orientation.